Hello PU2 champions, welcome to day 2 of 21 days challenge to get 95% in second PUC board exams. So as part of today's challenge, I have given you two chapters for homework. Number 1 was integral from maths and the second one was chemical kinetics from chemistry. So you have to revise these two chapters and practice its most important questions from the PDF I have provided. If you haven't downloaded the PDFs yet, the link is there in the description section. So please click on the link, visit the page and download the PDF right now. In this video, we will be discussing the most important questions from the chapter Chemical Kinetics, as this chapter can give you 12 marks in your final exams. Okay, all these questions are sourced from model question paper, question bank and from the previous year questions. So let's get started and understand the blueprint of this particular chapter. So if you see, the total weightage of chemical kinetics is 12 marks. Okay, now you have 1 mark from 1 marker question, 2 mark from, like, you'll get 1 2 marker question, 1 3 marker numerical question and 1 3 marker theoretical question and 2 numerical 3 marker question. I'll just clarify it once again. 1 1 marker question, 1 2 marker question, 1 3 marker theoretical question and 2 numerical 3 marker questions. Okay, so now let's talk about the 2 marker questions first. The first question is, mention 3 factors that affect the rate of the reaction. So concentration, temperature and catalyst. Okay, next question, state rate law and what is its SI unit of rate. Okay, so rate law, as you know, it is an expression, okay, which relates, or it is an equation which relates the rate of a reaction to the concentration of the reactants. Okay, so we know that concentration is a factor of rate of a reaction. So the relation between these two will help you to give the rate law. Next, crucially, the rate law for a reaction cannot be predicted from its stoichiometry. It has to be determined experimentally. And the SI unit is mole liter inverse second inverse. Now coming to the third one, what are elementary and complex reactions? So here you can see the difference between them. So elementary reaction takes place in one step, whereas complex reaction takes place in more than one step. Okay, and basically in elementary reaction, every step has its own, like, since it is a single step reaction, the overall order of the step is equal to the overall order of the reaction. But in complex reaction, each and every step has its own order. Okay, that is important. Next, we'll talk about what is first order reaction and write the relation between the partial pressure and the rate constant. So first order reaction are those in which the rate depends on the first power of the concentration. Means I can write like this, one second, rate is equal to K into A. Okay, rate is equal to K into A. So now this power of A, you can see if the power of 1 A is 1, then it is called a first order reaction. Now the equation for this K equal to 2.303 by T log of P naught by P, where P is the initial pressure and P naught is the initial pressure and P is the final pressure. Okay, now coming to next one, question number 5, differentiate between the order and molecularity. So here we have different points of differentiation. So definition, sum of the powers of the concentration terms in the rate law, that is called as definition. Molecularity is number of the reacting species colliding in an elementary step. Now possible values for order can be 0, fraction or an integer, whereas for molecularity it has to be always a whole number, 1, 2 or 3. Method of determination, determined experimentally, whereas molecularity is determined with theoretically. Application, if you see, it is applicable to both elementary and complex reactions. Molecularity is only applicable to elementary reaction. Now next question, for a first order reaction, For a first order reaction, plot a graph of log R0 by R versus time and write the value of the slope for this graph. So if you see the equation for first order, K equal to 2.303 by T log of R0 by R. Okay, now this log of R0 by R, this is a term and the another term we have is time, right? So what is time? I can write it as 2.303 by K log of R0 by R. Okay, now here if you see, this is equal to y is equal to, we need a plot for, okay, I'll just rearrange this equation like this, log of R0 by R, okay, is equal to K by 2.303 into T. Okay, so this is equal to y equal to m into x. Okay, so now here you can see this is the slope. So what is the m value? K by 2.303. So you can see here, and you have to draw that. It is a straight line equation. Okay, so you can see here like this, slope is equal to k by 2.303. Okay, next coming to question number 7 here, what is a pseudo first order reaction? Give example. Okay, a pseudo first order reaction is a reaction that appears to be first order but is actually second order. Okay, it appears as first order and then it is actually a second order reaction. It happens when one or more reactants is present in excess. Now, when one of the reactant is present in excess, if you change its concentration slightly, if you increase it or if you decrease it, it will not affect the rate of the reaction. So that is why that particular reactant which is in excess does not affect the rate of the reaction. So basically it is a second order reaction, but one of the reactant does not affect the rate of the reaction. So we consider it as a first order reaction. Examples are hydrolysis of ethyl acetate, inversion of cane sugar. Next, give two examples of first order reaction. We have decomposition of N2O5, radioactive decay. These are all first order reactions. Next, write the Arrhenius equation and explain the terms involved in. So now whatever questions I'm discussing, these are all 2-marker questions. So Arrhenius equation, K equal to A into e to the power of minus EA by RT, rate constant, frequency factor. EA is activation energy, R is gas constant, and T is temperature. Next, for the reaction H2 plus I2 gives 2HI, draw the diagram showing the plot of potential energy versus the reaction coordinate to explain the role of activated complex in the reaction. So this question is there in model question paper 1 of 25-26. So if you see here, this is the reaction. First, what happens? H2 plus I2 reacts with each other to give you a complex like this, that is HI is formed. Now after this, what happens? You have HI plus HI like this, two complexes are formed, but the main thing is the reactants do not directly get converted into products, they get converted through an intermediate. Okay, so that you have to show. This is the reactant and then there is one activated complex is formed here. Okay, and this then gets converted to the product. This is delta H or the reaction difference. Next is graphically represent the Arrhenius equation and calculate the activation energy from it. Okay, so if you see graphically represent the Arrhenius equation, we have K is equal to A into e to the power of minus EA by RT. So I have ln of K is equal to ln of A minus EA by R to 1 by T. Now if I plot this ln KY is equal to M, X and C. Okay, so the slope here is minus EA by R. Okay, and then 1 by T is present and then we have ln A. Okay, here we have ln A. Clear? Now slope value is there, activation energy can be calculated from the slope. You can see once you get the slope value and you have this slope is equal to minus EA by R. So from that we can calculate the value of activation energy. Next, plot the Boltzmann distribution curve and mark the position of EA. So you have to draw this diagram and the position of EA you can mark it somewhere here. Okay, this is the position of the activation energy. Next, what is the most probable kinetic energy? You can see here something is marked as most probable kinetic energy. So what is it and how does it change with temperature? So actually most probable kinetic energy is the kinetic energy possessed by maximum number of molecules. Okay, with the increase in temperature, this most probable kinetic energy value increases. Clear? Next, explain the effect of temperature on the rate of the reaction using graph. Okay, just a minute. Yeah. Explain the effect of temperature on the rate of the reaction using graph. Okay, so you can see as the temperature increases, the rate of the reaction also increases. So what happens is as the temperature increases, the number of molecules having energy more than the activation energy increases, and that is why the rate of the reaction increases. You can see this graph properly. You can see that when the temperature is T, okay, only this many particles are having energy more than the activation energy and only this many particles can form the products. But when you increase the temperature to T plus 10, the number of particles having energy more than the activation energy increases, and that is why we get and that is why the product number of particles which can now form products will be more, and that is why the rate of the reaction increases. Next, explain the effect of catalyst on the rate of the reaction. So catalyst lowers the activation energy. You can see without catalyst this is the activation energy and with catalyst this is the activation energy. Now if you have seen the Arrhenius equation, what we know, K is equal to A into e to the power of minus EA by RT, right? That I can write as A into e to the power of EA by RT. Now see, when activation energy decreases, this whole fraction will decrease. E to the power of a lower value, this whole value will decrease, and if this whole value decreases, K will increase, right? So that is why when activation energy we use, the rate constant increases. Next is question number 16. Write any two properties of catalyst. A catalyst does not undergo permanent chemical change, very important, and it increases the rate of the reaction without affecting the equilibrium. Next, what is activation energy and how does it affect the rate of a reaction? So activation energy is the minimum energy required for a reaction to occur. So what happens? The reactants first gets converted to an activated complex, and that activated or that intermediate complex forms the products now, right? So the energy required for the reactants to convert into activated complex, the extra energy that we need to provide, this energy is called as the activation energy. Next, lower activation energy means faster reaction and higher activation energy means slower reaction. What is a catalyst and whether catalyst catalyze non-spontaneous reactions or not? So catalyst is a substance that alters the rate of the reaction without undergoing any change, and whether it catalyzes the non-spontaneous reaction, no, it only can catalyze spontaneous reactions, not the non-spontaneous one. Next, according to collision theory, give any two criteria for effective collision. The first criteria is that the colliding molecules must possess energy equal to or greater than the activation energy. And second one, the molecules must collide with the proper orientation. Next, give any two drawbacks of collision theory. The first one is it considers the reactant molecules as hard spheres and do not consider its actual structure is not considered. All the reactants are considered to be spherical form. Second is it is applicable only to gaseous reactions, and third one is it fails to explain the reactions of complex molecules. It can basically explain the elementary reactions but not very much applicable for complex reactions. Next, what is collision frequency? Give the equation that represents the relation between collision frequency and the steric factor. So you can see collision frequency is the number of collisions occurring per second per unit volume. It is denoted by ZAB. Okay. Now K is equal to PZE to the power of minus EA by RT, where P is the steric factor, Z is the collision frequency. Next, what is meant? Now we will move to 3-marker question. What is meant by chemical kinetics and write its two application was the full question. This is from model question paper 2. Okay. So in model question paper 2, there was no derivation asked. This was asked instead. So chemical kinetics is a branch of chemistry that deals with the study of reaction rates, the conditions under which the reaction rates can be altered, and the mechanism of chemical reactions. And what are its application? It is used to determine the speed of a chemical reaction, and it also helps to describe the condition by which the reaction rate can be altered. Okay, two things: to determine the speed and what changes we can do so that the reaction speed can be changed. Next will be the derivation. So there are 4 important derivations in this, 5 important derivations. First is the 0th order, first order gas-phase reaction, half-life of 0th order and half-life of first order. Okay. So derive the integrated rate equation for 0th order reaction. So for a 0th order reaction, let R gives you P. Okay, this is the reaction, and we know that if it is a 0th order reaction, rate is proportional to R to the power of 0, or rate is equal to K into R to the power of 0. Now R to the power of 0 is equal to 1, so I can write rate equal to 1, rate equal to K. This is the first equation. Next, where K is rate constant of the 0th order reaction, rate is also defined as minus dr by dt. Minus dr by dt is equal to K. Now see, this rate, for this one I can write rate is equal to minus dr by dt, and we have minus dr by dt is equal to K value. Rearranging the equations, we get dr, we have K dt. Okay, and integrating the equations, you will get now R is equal to minus Kt plus I. R is equal to minus Kt plus I, where I is the integration constant. Now our thing is to find the value of I. So to find the value of I, you have to put T equal to 0 and R is equal to R naught, where R naught is the initial concentration of the reactant. So what was our equation? R is equal to minus Kt plus I, right? So I'll just put R, instead of that I'll put R naught, and Kt will be 0, so I will give me R naught value. Now substituting the value of I in this equation, that is, this is my equation number 4. So I'll just substitute I value, which is R naught. I'll get R is equal to minus Kt plus R naught. Rearranging it, Kt is equal to R naught minus R. And then K value will be equal to R naught minus R by T. This is the integrated rate equation for the 0th order reaction. Now next question is to derive for first order. Very similar process. Suppose this is the reaction, R gives you P, and for that rate is equal to K into R. Rate is equal to minus dr by dt. Okay, now I can equate these two equations and I'll get rate is equal to or minus dr by dt is equal to Kr. Okay, you can see in both this equation, left hand side is same, so our right hand side will also be equal. So this is the final equation. Next, rearranging this, I'll have dr by r is equal to Kt minus Kt. Right, now you can take integration on both sides, so we'll get ln r is equal to minus Kt plus I. So now at T equal to 0, R is equal to R naught, initial concentration of the reactant. So you have ln R naught is equal to minus Kt plus I is equal to ln of R naught. Now substituting the value of I in equation 4, we will get ln R is equal to minus Kt plus ln of R naught. Clear? Now we will have arranging this equation, Kt is equal to ln of R naught by R, and converting the natural logarithm, will get 2.303 into log of R naught by R. Now if you just arrange it equation, K will be equal to this one, and that is your equation for the first order derivation. Now this question is very important and was asked in 2024 pre-board paper. Okay, derive the integrated rate equation for gas phase reaction. Okay, this is very important. We get confused when it is shown first order. Students generally derive this particular derivation, but if it is gas phase reaction, the derivation is entirely different. Okay, so please see here how to do it. So I'll show you. See, first let the reaction is A gives you B plus C. So at time T equal to 0, the only pressure we have is Pi, which is the pressure of A, and 0 and 0 here. Then as time passes, X amount of A has reacted, so A will be Pi minus X, B will be X, and C will be X. B and C are formed here. Now where X is the decrease in pressure of the reactant A at time T and increase in pressure of the products B and C. Pi is the initial pressure at time T equal to 0. Pi is the initial pressure at time T equal to 0. So you should mention what all terms you have taken. Now at time T, what is the total pressure? Total pressure is Pi minus X plus X plus X. So XX will get cancelled. Total pressure is Pi plus X. Now X is equal to Pt minus Pi, right? So Pt is the total pressure at time T and X is equal to Pt minus Pi. Now but at time T, Pa is equal to, that is the pressure of A is equal to Pi minus X. Now Pa is equal to Pi minus, what is the value of X I have calculated? Pt minus Pi. So Pa is equal to Pi minus, so you can see minus Pt plus Pi, and the final equation 2Pi minus Pt. Okay, so now I'll just see the equation for this particular reaction. K equal to 2.303 by T log of Pi by Pa. Okay, Pi by Pa. Now Pa is what? Pi minus X, and you have already seen if I substitute, I'll get 2Pi minus Pt, so that you have to substitute here. Next is show that the half-life of a first order reaction does not depend on the initial concentration of the reactant. Okay, so we know that the integrated rate equation K equal to 2.303 by T log of R naught by R. Now when you're talking about half-life, at that time what will happen? The initial concentration becomes half, right? So you have to substitute T equal to T half and R value is equal to R naught by 2. Here this R value is nothing but R naught by 2. So I'll substitute that. If you see, 2.303 by T half log of R naught by R naught by 2. So this 2 goes up here. Log 2 is 0.3010, and now if you multiply this, K value will be, sorry, T half value will be 0.693 by K. Now if you see in this particular expression, depends only on the rate constant, right? The T half value only depends on rate constant and not on the initial concentration R naught. So the half-life period of the first order reaction is independent of the initial concentration of the reactants. Next is show that the half-life of zeroth order reaction depends on the initial concentration of the reactant. Similar process will do for zeroth order reaction. We know that for zeroth order the integrated rate law is R naught minus R by T. Now here if I substitute T is equal to T half and R is equal to R naught by 2, and now if you solve this one, you will get here, I can just solve this as R naught by 2 T half. K is equal to R naught by 2 T half. Now what will happen? T half will be equal to, I can just say that I can just arrange this one, it will get R naught by 2K, rearranging the equation. So you can see this shows that the half-life period of a zeroth order reaction is directly proportional to the initial concentration. Okay. Next, we'll go to now numerical questions. So I have taken the numerical questions of model question papers as well as the PYQs. So the first question was from the model question paper 1. Okay, very direct question. The first order rate constant at 600 Kelvin is 2 into 10 to the power of minus 5 second inverse, and the activation of energy is 209.8 kilojoule. Calculate the rate constant at 700 Kelvin. This is according to the Arrhenius equation for two different temperatures, like log K2 by K1 is equal to EA by 2.303 R 1 T2 minus T1 by T1 into T2. Now here what happens? T1 is 600 Kelvin and T2 is 700 Kelvin. T1 is 2 into 10 to the power, K1 is 2 into 10 to the power of minus 5. So I'll substitute all these values. Log of K1 I have written here. EA value is given to me 209.8 kilojoules. So do not forget it to convert it into joules. Then once you calculate it, you will get 8.124 into 10 to the power of minus 3 second inverse. Okay, calculation also don't you have to worry. Calculator is there with you. You can complete the calculation. Next, we'll see question number 46, again from model question paper 1. Okay, I have taken the same question which is there in your model question paper so that you can check. Analyze the given graph, drawn between the concentration of reactant in moliliter inverse versus time in minute. Calculate the average rate of the reaction in terms of minutes and seconds. Average rate of the reaction, right? So you can see, you can calculate any two value. Average rate is what? Change in concentration by change in time, right? So for example, if you have this particular time 0.4 and 0.2 if you are considering, okay, so 0.4 and 0.2, the time value is what? The time difference is 10 minutes, right? So I can write 0.2 minus 0.4 divided by 20 minus 10. So you will get plus 0.02 mole minute inverse. Now if you convert it into seconds, just multiply this one by 60, you will get 3.333 into 10 to the power of minus 4 molar second inverse. Okay, so what is the average rate here? 0.02 molar minute inverse, and we can convert it into 3.333 into 10 to the power of minus 4 molar second inverse. Next question is from the model question paper 2 here. The rate of the reaction quadruples. So this is also from Arrhenius equation. When the temperature changes from 293 to 313 Kelvin, calculate the energy of activation of the reaction assuming that it does not change with the temperature. So this time the same formula we will use, but we'll calculate activation energy this time, right? So this formula is already there. It quadruples means K2 is 4 times of K1. K2 is equal to 4 times of K1. So just substitute all the values here, and if you just calculate this EA value, you can have, again, you have calculator, you don't have to worry at all. So log 4 is 0.6021, and please remember log 2, log 3 and log 7 and log 5 value. Okay, so if you know these 4 values, you can able to calculate for any other value. Next, this if I solve, I'll get 52.86 kilojoule per mole. I'm not going to solve it in detail, I'm just explaining you how to solve it. Next, we'll see the question from model question paper 2 only. This is from integrated rate equation. The carbon-14 content of an ancient piece of wood was found to 3 by 10th of that of the living tree. Calculate the age of that piece of wood. Half-life is given to you. So you know all the radioactive decays are first order reaction, and the log 3 value is also given to me. So what I can do here is I can first calculate from the half-life the K value, right? So what is K? T half is equal to, sorry, I have T half is equal to 0.693 by K, right? So what will be K? K is equal to 0.693 by T half, right? So 0.693 by T half 5730, this is my value of T half, sorry, K value. Okay, now for the first order reaction, we know the formula 2.303 by K log of R naught by R. Now what is this R value? See, the residual, it is 3 by 10th of that of the living tree. Means if the living tree, the concentration is R, then in that piece of wood, it is 3 by 10th of that. So that is the formula, R is equal to 3 by 10 of R naught. Now if you just substitute all this value, you will get log 10 minus log 3. And once we substitute all these values, we will get 9960.6 years. Okay, 9960.617 years approximately. Now coming to question from model question paper 3, our first order reaction has the rate constant of this value 2.3 into 10 to the power of minus 5 second inverse at 500 Kelvin. At what temperature the rate constant of the reaction becomes this value? Okay, again this is from Arrhenius equation. Two rate constants are given, one temperature is given, you have to find the other one. The activation energy is also given to you, rate R value is also given to you. So again we will be using the same equation, log K2 by K1 is equal to EA by 2.30. So we need to find this T2 value here. So K2 value, you know, 17.25, that is substituted here. K1 is 2.3, that is substituted here. EA value is 191.472 kilojoules. So just multiply with 10 to the power of 3. 2.303 R value is there. T2 value is there. T1 value is how much? We know 500, and 500 into T2. Now if I solve this all and find the value of T2, you will get 551.73 Kelvin. Next, we'll talk about model question paper 3, second numerical. A first order reaction half-life is 23 minutes. How much time will it be needed for 30% completion of the reaction? So again, half-life value is given. From that, you can calculate the K value, right? So that will be 0.693 by 23, which will give you this value, right? This is your half-life K value from the half-life we have calculated. Next is 30% completion of the reaction. 30% will be completed. That means how much will be remaining? 70% will be remaining. So R is 70, R naught is 100. So just substitute this value and you will finally get 11.82 minutes here, right? Next, we'll solve the question from 2025 paper. Actually, this question was there in 2025 paper. The rate constant of the first order reaction increases from this to this when the temperature changes from 300 to 310 Kelvin. Calculate the value of EA. Again, from Arrhenius equation, K1 value is there, K2 value is there, T1, T2 values are there. Just write this Arrhenius equation, substitute everything, and then when you calculate the EA value, you will get 53.6 or 59 kilojoule per mole. Next is another question again from the first, I can say, a 2025 March paper. The initial concentration of N2O5 in the following order reaction is given. Okay, was this much. The concentration of N2O5 after 60 minutes is this much. Calculate the rate constant of the reaction at 318 Kelvin. So this is direct integrated rate law for first order that you have to apply. K equal to 2.303 by T log of R naught by R. R naught value is given to you 1.24 into 10 to the power of minus 2, and R value is given as 0.2 into 10 to the power of minus 2. Now if I substitute all this, we will get log of 6.2, and if I solve the entire value, we'll get 0.0304 minute inverse. Okay. Fine. So children, this were the most important questions from the chapter Chemical Kinetics. I hope all of you have understood all the questions. If you have any doubt, please just let me know in the comment section. I'll help you to, I'll clear all your doubts. And yes, if you haven't like downloaded the PDF of this important questions, the link is there in the description section. Please go and download first. And as I told you, this important questions you need to first practice and then come and check the solutions. Do not directly watch this video. Please solve it, and this is very, very important. And if you have done this one particular video, your entire questions of chemical kinetics will be done. Okay, there won't be any other questions. We'll be making a separate video on MCQs that will be live at 6 p.m. so you can join that. Thank you so much. And yes, let me know in the comment section what is your status about the day 2 challenge. Have you started, completed, in progress? Just let me know. Thank you. Bye bye. Take care.